So, this video is intended to be a kind of school maths video, and actually, I should be taking it in German, but knowing that German is an obligatory subject, uh, at English, I mean, English, of course, is an obligatory subject in German schools. I'm just taking the liberty to do this video in English because those pupils would be really interested in the topic, they will probably know English because they would like to go further to pursue further mathematics in their career or at least engineering studies. That's what I would assume, so that one would need English anyway. So that's the reasons why this video is in English nonetheless. Yeah, I don't have that much uh, lust to do a video in German. Right. Okay. So, what are we talking about? We'd like to look at the very basics of the trigonometry and of inverse trigonometric functions, as well as of geometric interpretation of complex numbers. Everything presented in a very plausible way, or at least, well, I see it as plausible. Let's see if you do too. I don't know if this video is of any interest to anyone other than people who would like to refresh some school maths in some, well, let's put it like that, in some fashion where everything makes sense. At least I would characterize my approach in that way. Right, so what will we do? We'll just recall sinus and cosinus first. Maybe when we are at it, also tangent. Well, oh, let's not go ahead of ourselves. Let's look at first part, trigonometry within right-angled triangle. Well, of course, everyone is familiar with that, but just for this treatise to be self-contained, I'll do that too. Especially considering the fact that we will refer to it later explicitly. Right, so consider a right-angled triangle. Well, not right choice, but okay. A, B, C, and that's the right angle. Then, of course, if we take an angle in that triangle, an angle alpha, then let's pay attention that the side that is in front, or well, I mean on the other side, if you look out of this angle into the triangle, which side you see, this side is called as the letter at this angle. So this is side C, this is side B, and this is side A. You can also just see that you have to add the letter in the three letters if you read from one angle to other, so that the letter for the side just completes the letter C. But this is just notation. It's not state that because it's really boring, right? Oh, this is really boring. This is just notation. All right, then we just define, and this is really just the definition. To such an angle, we assign two certain numbers which are computed in a special way. And we call these numbers, when the angle is given, the angle alpha is given, and we call this number sine alpha, and sine alpha is supposed to mean exactly, well, that's b divided by c, and pay attention to how I choose b. B is the side which is on which the angle doesn't lie, which the angle doesn't touch. So that is the sine, and the cosine is correspondingly just that thing, that quotient, where we take the side on which the angle kind of lies, or which the angle touches, right? This is cosine, and we always take the quotient to c. Well, you know that this is the longest side in the triangle, in the right angled triangle, and well, you can memorize that just thinking, well, I have my cosine always in absolute value. That is, it is absolute value smaller or equal 1, and that is, it is smaller or equal -1, smaller or equal bigger or equal -1, smaller or equal 1, and same for your sine, right? All right, so this is sine, and so I can just write those inequalities like this, and it is clear what that means, right? Yeah, giving bounds for this sine. Right. Well, this is actually maybe an interesting question. Why? How do we know that C is actually the longest side? Well, you could say the longest side is always in front, I mean this, if you look out of the angle, we see the side, in front of the largest angle, right? But how do we actually prove that? I wouldn't know the answer right away, I guess. Let's just, what I would do to just convince myself that it is the case. Let's think about that. Wow. Of course, we could do it like this. Of course, the very simple way, you know the Pythagorean theorem, and you just know. Uh, you just know by Pythagoras. That will be actually important for us too. With Pythagoras, you know that C is equal square root of A plus B squared. For the proof, you could, for example, refer to the geometric proof, right? Right. Well, in the case you don't know, the geometric proof goes kind of like this. If you have, well, it's kind of self-suggestive, right? You have here C, right? And then you draw this, and this is C, and you have to have a square with this side length, because this could be rewritten as squared plus B squared, right? And then you have C here, you have C here, you have C here, right? So if you have such right angle triangle, you could draw it like this, and then you would see that you have exactly to draw this to be complete thing, and you have that, and you have that, and what do we see here? Well, we see that this exactly A, and this is exactly B. This is exactly well, maybe I have missed it, but it's just the error, right? B. This is A. This is B. Well, maybe you can't see that clearly, but it's clear what I mean, right? And this is A plus B squared. And this is C squared, and you have just to wait, how did it go? Right, we have to show that the R of equal area, right? So let me think for a little while. So we'd like to show that this is same area as this here, right? And we could just to stay geometric, we'd like to actually subdivide this into exactly such triangles, right? And if we do that, all right, right, okay. So you can draw it properly, and then you'll just see that this here occurs. Right, and this is exactly before triangles that you see here, right? Okay, but this is just playing around. Of course, I would not like this proof. Well, if you like draw something like this, I mean, this is B, this is A, and then you draw something like this, right? Okay, that was wrong. This is B, of course, and this is A. And then you draw something like, well, here you have B, here you have A. I mean, what am I doing? I mean that above can be made. Can be done properly. Oh. Okay. I'd like to do it properly once. Alright, so if we take, for example, A equal to this, and we take B equal to this, and we can draw that like that, right? Then we draw here A again. Then we draw here B. And then we go like this. Right? This works. And now we'd like to actually... Huh. That's funny. It doesn't seem to fit like that. Okay, that is now funny. Oh, surely. Ah, No. Now I get it. Okay. We have to draw. Okay. Alright, if we would have that like that, right? That would be C. And then of course this wouldn't fit like this, right? So we have to draw with a little delay or replacement, right? So we draw that that is C, and that is again A, B. Now that is C. I'm not getting it right. Okay. Right, we have C here, here, here. I should really draw it properly, otherwise it won't work, but maybe I'll show you better the analytic proof, but I mean geometric analytic. But if we are already at it, let's try to derive it properly. Right, the thing is, when we have such a square, okay, that's again not quite a square, but okay. So that is C. And well, we just draw the triangle as it is, right? Okay, one really needs a square. Otherwise it won't work. Okay, so not here to draw squares, but doesn't matter. Okay. Then you have to have a right angle here, right? We have to have that here, and we have to have. Okay, I think I can't draw it exactly. Okay, so okay, I know. We can really take something that makes more sense, right? So here we have 6, here we have 6, we have 6, here we have 6. We could have actually taken also, yeah, let's do that. Because that would be even better. Let's take that. So I'm trying to have Egyptian triangle. With proportion, of course. We have nice things. Right. Well. And now we are interested in the right angle. Okay. Now of course we have to draw that. Like that. Oh. We have right angles. Okay, well, that's a little bit difficult. So, all right. Well, of course I shouldn't do that because we should first give a triangle. We should. I should look at it. Okay. Rough. Yes. Okay. Let's take a triangle like that. And let's consider the C. And let's look at how that. Alright. Now of course we have to show that this gives exactly same thing, right? So we have to show that this square gives actually same as a squared plus b squared. So now we have to consider smaller things, smaller squares, right? Oh, I made a mistake here, of course. Okay, well, now I get it. Now I get it. That totally makes sense. Okay, now I'm a little bit tired. That was nonsense. I would have proved the wrong thing. Ah, no, now I get why it didn't work that well. Yeah, okay, makes sense. We are trying to prove, of course, that c squared is equal to a squared plus b squared. And some nonsense that I had there. Right. It was similar, but well, what was written, drawn there, it was a different thing, right? So I thought that it is something weird, but okay. Well, now you see what we actually have here. We have A, we have B, we have A, we have B, we have A, we have B, we have A, we have B. And now this is, of course, the total. Okay, let's call it A, B, C, D. So, the area of ABCD is equal A plus B squared is equal A squared plus B squared plus 2AB. Right, just use the formula. Alright, and now we have that C here. And we have to find those two ABs. And we have to show that if we subtract those two ABs, that what remains is exactly that C squared, right? And then since that is the total area, then we would have shown that this is actually equal to this. Right, now let's find those two ABs. Right, and well, those are exactly, if you recall, you just have to compute the area of a triangle. You just have to take A multiplied by B divided by 2, right? In general, height multiplied by the ground line with the ground side in which you have constructed that height divided by 2. But here we have 4 such things, right? 4AB divided by 2 gives exactly 2AB. And this is what? This is exactly ABCD, the area of ABCD, minus C squared. So we have that what? Yes, exactly. So if we now here take this and we put it in here, right? This ABCD minus C squared. Here we replace that. We replace 2AB by that. And then we subtract on both sides A, B, C, D, and we bring C squared on the other side, which results in C squared equal B squared. Right, but maybe let's consider another proof, which is more geometric. Okay, and that goes like this. I actually wouldn't know right away how that is done. I probably what would I do? How would I prove that? That's a good question. Well, of course it's course, we have that it is just a simplified case of the cosine theorem, right? But this is not what we'd like to have. We'd like to show that directly, right? Using some geometrical stuff. How would we prove that? Not with this proof, but more rigorously, so to speak, because here the picture plays a direct role, and this is of course problematic. We would have to show that this is reconstructible and things like that, right? Well, actually it is, yes. But wow. How would I like to see it myself? Well, yeah, that's interesting. Let me think a little bit. Maybe. See. Okay, we could do vectorial proof, of course, which is also not quite nice in that regard. Right. Oh, we would just do some vectors and we would take, well, okay, okay, there we would again use Pythagorean, okay, this theorem is really basic, we have to show that. Okay. Let's show it really properly. I guess so that we will need a circle. Alright, well, let's say this is a circle with the radius r, right? And just know that this is right angle, right? Actually, this also requires a proof, right? That this is a right angle. Oh, of course, we know that this angle is half of a 180 degrees angle. But of course, we'd like something more substantial. Why is that, right? And well, okay, but let's just twice angle and the diameter equal to pi half. Right, and the question would be here, any angle diameter equal to pi half. Oh, but let's imagine we have that, all right? Imagine we have that. Could we prove that easily? Well, using some theorems, yes, but without anything. How could we prove that thing? Wow. What proof would satisfy me? That's the question here. Of course, we could symmetrically um, but let's take it for granted for a second. Take for granted. Um, the thing is, to prove something like this, okay, I don't know right away how to prove it. Wow, that much for uh, having everything presented in a plausible fashion. Okay, I have to think myself. Uh, what assumptions do I like well enough, which we'd like to deduce that? Well, hmm, actually would like to deduce it from axioms because it's a very simple statement, right? But to that we have to go backwards. Right, so, okay, now I'm intrigued. How would I show that myself? How would I show that? I was asked to prove that. How would I show that? Hmm. Yeah, sometimes simple stuff doesn't seem to be that simple. Okay. Mm, if we are not allowed to use geometric visualization, right? And what could we do? Right, but what does it mean we are not allowed? Well, in this case here, it doesn't look quite nice, right? Um, a question that I'm wondering about is whether lengths here are determined, and the answer is yeah, not, because I could take something and I could rotate it of same length always, and I could rotate it differently, right? So the two angles are not determined. So if I put it like that, I get this angles. If I put it like that, I get this angles. So we, of course, we hypotenuse and right angle. It does not determine the whole thing, because I could draw it like that with a right angle, right? I could draw it like I mean, I draw now some side which is totally not anything but not parallel to this side, and I'll find a point at which we will have right angle here. I'm now drawing another side, and I'm trying to play with them so that you will have right. But would those not be similar triangles? Let's check that. Not just similar, but similar with coefficient 1. Let's check that. We take any two triangles, draw any two right angled triangles taken with that, right? And we have that they already have angle. Okay. And then they have they share the hypotenuse, right? And now we'd like to show their similarity if they are similar, right? And we'd like to know if they're similar, right? But we don't have that the hypotenuse is along the side yet, so we would not know it necessarily. All right. Yeah, let's start here. All right. Does hypotenuse and right angle determine the triangle, the length of hypotenuse and the right angle? The intuitive answer is actually yes. But on another hand, this is this length, right? And this is this length. This length is equal to no, obviously no, because if we go like that, and somewhere here, if we have a circle, we have something very small, right? And that here will be, so no, for example, for such a hypotenuse, we can always draw something like this. Right, so no matter what length of hypotenuse we take, we will find the possibility to draw. Of course, let's look at that. We consider the middle be orthogonal line to that. And obviously, as we go on it, obviously those sides are equal, and obviously the angle will increase gradually, right? Angle would increase gradually as we go on that. And at some point, and well, those two angles would increase as you wish. And at some point, the angle would achieve 90 degrees. Right, because we can continuously increase that. And so at some point we would be at 90 degrees. So what we have is actually that hypotenuse and right angle do not determine the triangle, because we could have hypotenuse of same length, and we would now go on this line, right? Now go on this line, and we would now go on this line. And you can see here the angles are certainly not 45 degrees, right? But it is, and clearly we can take any length of hypotenuse. Okay, so hypotenuse and right angle do not determine, we have proved that. Well, I mean, we have plausibly seen that, do not determine triangle. Okay, so here, despite the badly drawn circle, there are different triangles possible. Okay, but despite that all, we would always have that a squared plus b squared is equal to c squared. Okay, wow. Let's try to prove it. So you see, this is kind of funny because it does not determine this triangle, so I don't like this. I didn't like that immediately, and it didn't change, right? So now I'd like to understand why this angle is actually the right angle. Well, we are on the diameter, and we know well that this angle is now 180, and this angle is the half of it. But why? That question we'll try to answer now. So, okay. For that, we would just show that this angle is actually half of the corresponding angle. That is given well, that is given what? Let's see. Okay, that angle is half of the angle. That is given as spanning here, and that is, well, this angle And we take just any angle here, and we take now this is, you see, this is angle from the center, right? And we take equal angle but spanning okay. We just showed that this angle is 90 degrees because it is half of this angle, of this open angle, right? And for that, we would just show that for any angle that is actually true, that if we have an angle like this, measuring something, alpha, then this is exactly half of the, wow, and now I'm not sure how to, actually, if we take that like that, then this is exactly half, this is the middle of the circle, exactly half of the angle if we take alpha here, right? So alphas are under each other. Right, and well, we have to show it for all angles. Or we could start, or we could also actually show it directly for the right angle, or we could try at least, right? We would have, oh, well, no, we cannot. We cannot show it for the right angle directly because that just would not work. Right. Instead we would have to show and if we are positioned here and here, okay, I shouldn't draw the right angles immediately because we don't know yet formally that it is right angles. It could be any angles, right? And then what do we do to actually show that it is the right angle? Well, what I would do, I would consider that this is that and that, right? And then I would take this, and I would know, right, that this is orthogonal to the radius, and this is orthogonal to the radius. You see, this is just because this is how a radius and the tangent to the circle behave. So this is basically what I'm taking as axiomatic, or um let's see if we can prove that the radius and the tangent are orthogonal to each other. Well, the thing is, the radius the radius is certainly the line of a shorter distance from this point to this curve, and then oh, the radius to a point at which the tangent touches, right? We have that point, at this point the tangent touches, and we have to show that this is orthogonal to this. Well, I don't think it is possible to show that. Okay. I would do a proof by symmetry. I would do a proof by symmetry, and I would just, without loss of generality, consider, since everything is symmetric, it really suffices. So yeah, the keyword is just symmetry. Or we could take the unit circle. And we could take the tangent. Yeah, okay. Okay. I would really, but yeah, the thing is, I don't know if that, but okay, we would have to prove that it is actually a tangent, right? If we would take some derivative, we could, if we would have written down the circle function, that's two square root functions, we would take the half circle, right? Because it just works. We could take half circle, and we could take some point in the half circle, and tangent to it would be tangent to circle at this point. We could compute the tangent explicitly, but that's not what I'd like to do. It's too much hassle, right? What I would like to do, I would like to just show that if this tangent isn't parallel to x-axis, to a y-axis, then we would have a point in which it cuts the circle, and how the unit circle. How would I do that? Well, okay, that I would really do by that, but maybe not in the way you expect. I don't know yet, but I guess that would be pretty simple. You see, let's imagine that we have a tangent that is somehow ax. Oh, okay. Our tangent is supposed. Okay, how do we do that? It's supposed to go through the point 0, 1, right? Through the point, because it is tangent at this point, right? 1, 0. Through the point 1, 0. Then, of course, we have ax plus b for the tangent. Let's call it tx, x plus b, and then we have that t of what t0 is equal t1 is equal 0, right? Because the tangent is just supposed to go through this point. Right. Oh, we could have just translated that to that. That would be x minus 1, but it doesn't matter. I could do that just as well. Right. Well, that would be a plus b. That would give us a is equal minus b. That's what I mean. We would just have translated that from 0 by 1, which is exactly the same as ax minus 1, which we have obtained now, right? So this tangent has now this equation for some a. I don't pose any restriction on a now, right? And the circle has the equation x squared plus y squared is equal 1. Well, of course, we are interested in the no, we are interested in both. We are interested in the upper half and the lower half. And this is just y equal, of course, it's not meant as a function, it's meant as two functions, right? But I'm just writing that like that, no problem with that, right? 1 minus x squared, and of course, x squared is, x is supposed to be, to have a coordinate. Minus 1. This parameterizes the circle, right? And we would now like to have our actually only a, because we are just supposing there is such a function, right? And we want to have a contradiction if a is, well, for any a, there should be a contradiction that this will actually cut the circle somewhere. And this is simple because this simply gives us that. And wow, this is the point where the line would supposedly cut the circle. If it wouldn't cut the circle, so it's supposed to be a tangent, then the only this point would be the solution, right? This point is wait, 0, 1. 0, 1, and this is supposed to go through this point. This is okay. And now we look at this, and we have 0, 1. This is okay, right? So this point is here, right? And this point is supposed to be the only solution. The point, let's write it here. 1, 0, I mean. Not 0, 1, of course, 1, 0, right? Because x coordinate 1, y coordinate 0. Right, and here we are interested in solving this. Right, how do we solve this? Well, we just square. Of course, that might okay, let's solve it maybe first. Oh, well, let's first square and see what comes out. Of course, if we would have this, well, no, it depends. Okay, we wouldn't have that uh, easily put. All right. Well, or maybe we'll do it even differently. We'll suppose that. No, we'd like to show that there are no solutions, right? We'd like to show that there are no solutions, and so adding solutions, which we did here, we would add solutions, wouldn't anything. So there are no solutions means that there is some contradiction, right? Let's see what this gives. 2x plus 1, 1 minus 2. And what we have here is just no solutions except for this one, of course. The one is on path if we have taken this line like this and it is on a circle. Anyway, I mean 1, 0. Always mixing that up. Right, a2. Okay, what do we see here? Here we have a2x plus 1. Here we have that. Okay, let's simply solve that. Because we can solve that then, right? And we obtain a2 squared x squared plus 1 x squared, right? We obtain minus 2a squared minus 2a squared x plus a squared. So, and we solve this. Well, I don't like ABC, even though it is a nice formula, but I just don't like it. So I do PQ, right? And we could also derive the PQ formula, but okay, I will leave that. Maybe for another, but okay, it's two. Okay, one has to see that one time maybe, but it is really simple, so I won't do that. I mean, this is equivalence. This is equivalence. This is that, right? All right. And we have that, and we have x1, 2 is equal minus that divided by 2, so by PQ we have this one, right, no problem here, plus minus square root of what exactly? Well, we have to square our thing here, alright, and we obtain a fourth squared plus 1 squared, and here we obtain minus qa squared fourth, right? And that square root is equal to what? Well, see, that is equal to, well, have to multiply that by that to have common denominator, right? So is that right? Yes, seems to be right. And we obtain minus 1 because I have multiplied that by minus a squared. Oh, that's a problem. That's a big problem. That's a big problem anyway, because it shouldn't be like that actually, because at least one solution we should get, right? For any such line, we should get one solution. So it is a problem. Well, let's see where we had the problem. I mean, 0, 1 should satisfy this. 1, 0 should satisfy this. So what's going on here? Okay. Yes, and it does, like, right? 1, 1, 1, 1. No, it does not. Yeah, something is wrong. Well, 1 equals 0, even for 1, 0. What? Okay, that shouldn't be like that. As you can imagine, okay, this was supposed to be that, actually. I mean, of course, this goes that, and then there, here is equivalence. All right, so have I got something wrong here? Plus 1, 1 minus x squared. Okay, 1 minus x squared plus minus. Okay. Wow. Here it still does, right? Yes, it does. Okay. I am confused because, like, where did I forgot the one. I forgot the one, right? Because I brought that to the other side, but I didn't bring 1. Okay, wow, that makes sense. Okay, well, then the whole thing here is that plus x squared, we brought this to here, we had that here, right? We had plus a squared here, and we brought 1 to here, and we divided here -1 just occurs because we have divided everything by this. And of course, to divide everything by this, we have assume, so those cases have to be considered separately. Assume R is unequal plus -1, right? Because if it is, sorry, it's not 0 anyway, so I then don't have to assume anything, right? Because we square. All right, and here we have in -1. All right. And what we actually get when we multiply that by that, I use the formula, binomial formula, and what we get here is, okay, that was a mess. But well, now it is corrected. And what we get is a fourth, 8 to the power 4, minus, here I use the formula in that I multiply that by another factor of this kind, right? So here we get then a fourth minus a fourth minus plus 1, minus a fourth plus 1, because this a squared minus 1, I have to multiply by that to have common denominator, right? And this is a formula, you can just multiply it out and you see the formula, a squared minus a fourth minus 1, and that is then that. All right. So the square root is extractable. Right, but what does that give? That gives exactly a squared plus 1, because this is positive, so we can do that. And if we subtract that, we get a squared plus 1. Right, this is minus, right? This is minus, this is plus, okay. That seems right. Now that is continued from here, or better from here. And we get that. All right. And if we bring, I mean, this is the result of this root, right? All right. Then we have plus minus. And if we bring that to that, okay, the denominator is already same. We have one solution being 1. That is, we have the solution, a squared. So we have two solutions. And one solution is, this is not both solution, but this is one solution, the other solution. So this is just one, right? And 1 for x is what we wanted, because this is exactly one point where it intersects. And another solution is equal to, let's see what this is, a squared minus 1 squared plus 1. Wow. This is something interesting. So we have another solution indeed. And well, I mean, another solution means, at least in this equation, that there is another intersection point and its x coordinate is this. And now we have to check, of course, if it really works. So if it really works, we check it here, because here we have said, well, that was actually tx equal, well, let's call it circle, right? Circle of x is equal y. Circle of x, and those are the points of intersection. XS, call that, and this is the corresponding equation. And we got our intersection point 1 0 as should be. And perhaps because this is no equivalence, this is only this, and we found solution for this, and maybe it is not a solution of this. We have to look at that. As should be, and supposed another solution, which would show which would not should, which would show that our thing there is no ax plus b tangent at the circle and 0 1. So, and that is like from here we continue here. Let's check if it is this indeed solution. Right, for that we have just to plug in our supposed x, right, of the other intersection point, of the supposed other intersection point. Right, have a x s for supposed for intersection, whatever I denoted it like that, plus minus 1 minus xs squared, and that we want to check. And let's plug it in. We had a squared minus 1 divided by a squared plus 1, right? A squared minus 1 divided by a squared plus 1. And we had minus 1 here, and we had plus minus 1 minus a squared minus 1 here, and we had a squared plus 1 here. Right, what's that? Oh, well, let's look first at that. Equal to plus minus. This is squared, right? And that gives in 1. This is, of course, also squared. So I use, I bring, I create the common denominator by multiplying 1 in denominator and in the numerator in with this factor, right? And then I use the formula by this factor. So plus 2 squared plus 1 minus a fourth. Right, and that gives minus a fourth, so I use already that minus, right? And I use the formula here before that, of course. So that is plus 2a squared minus 1, and here the square root continues, of course, and here we have a squared plus 1 squared. something like this, right? And what we would get is, well, okay, -1, and here -4, and we would get 4a, okay, that would be plus minus, and that is, we have both possibilities at our disposal in this context. And okay, I don't have to write here that anymore because it is clear what the results, right? And what the results is 2a divided by a squared plus 1. And what's that here? Well, that is just a, and here I uh, subtract the fractions, right? And what is here? We get minus a squared minus 1. And here is our a squared plus 1. And we already see that this gives us minus 2a squared plus 1, which is a little bit funny. One could think it is funny, but because this is for plus, minus, and this is for minus, but this is just because we didn't choose the sign of a. We just choose it to be anything, right? Right, and if we would have chosen the sign of n in the formulations here, we might have gotten equivalence or something. Well, I'm just fantasizing, right? So that would have turned everything upside down. But here it just turns out that this is that. But that could be on the upper side of the circle as well as on the lower side, because depending on positive a or negative a, we would have intersection point here or here. But this works, and this indeed gives an y value that is the same for this x, and so we have two intersection points. So two intersection points for any t of x that can be expressed t of two intersection points for any t of x tangent at 1, 0, hence obviously linear, that can be expressed as linear, of course, linear function. But the interesting thing is function. If we have such a linear function, it is not a tangent. And so we should look for something that is not a function, but is a tangent. Well, what line is not a function? So what line in the coordinate system is not a function, but can serve as a tangent? Only this one line. So, and here we use an interesting argument actually. You see, hence, that's interesting, right? We prove it via hence the tangent line, because tangent is always a line, it's just the definition what tangent is. A tangent line through the unit circle at 0, 1, at 1, 0, at 1, 0, cannot have a representation as a function. Function in xy coordinate system. That leaves only the choice of a line y equal 1 as the tangent. So you see, instead of just saying a tangent line to the circle being orthogonal to the radius is an axiom, we have shown it first for the unit circle that it has to be, because, well, the x-axis is orthogonal to this, but we could also prove it like 2 lines. We could prove the orthogonality, right? But okay, yeah, here it's that obvious that, wow. But we could prove it like, I would like to prove that we could prove that this is instead orthogonal to this. I think it's obvious, but wow. Actually, it is defined to be orthogonal to begin with. This is the basic assumption of how we construct the orthogonal system. But we could come up with different kinds of proofs. You see something you have to take as an axiom. You could have taken this as an axiom. Or you can take the frame of the coordinate system, the axis being orthogonal, as an axiom. So you have to start something you have to take as for granted, right? And here we just take for granted that those two are orthogonal. But actually, we don't have even take for granted that. We can prove it just by saying, well, that for a line there is unique line that is orthogonal for a point. This is really an axiom, because this is, if I recall, this equivalent to the parallel postulate of Euclid. So to a line, this is equivalent to a line. There is only one orthogonal line to it through a given point. So this is really an axiom. This is Euclidean axiom, and that we know to be an axiom, right? And so we could just say, well, for any other line that is not this line, there is an angle to this axis, right? And this is just given by this A, right? Because we could also prove that because any such A line, right? If we take such an A line and take it through any point, and this is just translated this line, and we can control the angle of this line, and we just see visually that there is an angle. But of course, somewhere one has to start. For example, we see visually that there is an angle that axiomatically and is it reasonable? You could decide, but somewhere you have to start. And having only simple geometric axioms like the parallel postulate, well, I don't know if you get there. So here we assume some things, but well, I think the things that we left out or assumed implicitly, they were pretty decent. We could have assumed that immediately, of course, but well, I didn't like to. So I have shown one proof of that at least, analytic proof. It's very simple, right? And we have encountered interesting argument, like we can't represent it as a function, and there's only one line that we can't represent as a function, so this must be this line. It was fun, right? Okay, so well, with that we have proved it for unit circle, but um by translation of symmetry, this is by us also an axiom. By translational and rotational symmetry. Rotational and rotational symmetry. By translational, rotational, and size symmetry. By translational and size symmetry, that is, if we large objects in size, keeping the proportions, they behave in the same way. Translational and size symmetry, I call it here size symmetry. Of course, it's not the correct term, but I don't have that in mind right now. Translational and size symmetry of R2, this of our plane. Wow, XY plane. And rotational symmetry. Rotational symmetry of a circle. This proves orthogonality of radius ending in a point of the circle to the tangent line to the circle through this point, to the circle through this point, for all circles with all points on them. In other words, we have proved what we wanted to prove first. Okay, so radius is orthogonal, and that is how we mark that the proof is finished. This was proof of tangent to a circle orthogonal to corresponding radius. Right. All right. Oh, I recalled something. For our solution, we had, of course, also to check that since it is x on the circle, this x should be, of course, between -1 and 1, right? And that here, if we take a 2, here is our x, and this is, of course, between -1 and 1, because, well, you can just prove instead a squared -1, a squared plus 1. Well, you have to prove that it is bigger or equal -1. You have to add 1 and show that it is bigger or equal 0. And for the other direction, a squared plus 1. And you have to show that it is small or equal 1. Then you have to show that this is small or equal 0. And you just see that if you put that here, we have actually done it here. You obtain something smaller than 1, right? And here you have to obtain something bigger. Well, of course, you have just put this 1 and this 1 eliminates, so you have just a to the power 4, and this is so. this is done. A to the power 4 is bigger or equal to 0. So this was just showing that this is really a legitimate coordinate for a restricted function to this interval -1, 1, right? Here we had to do that, so that to be a solution that was also a requirement. So we actually have that as we liked, as we had to be able to that a solution. So it is really a solution. It's just a side note that we had also to check that and we forgot. Okay, well, let's we have proved that. Let's go back and try to prove what we actually wanted to prove. We wanted to prove something geometrical. We want to prove that this is actually a right angle, right? Here we have that orthogonality, here we have that orthogonality, and so we can use parallel lines. All right, that's good. All right, well, we want to prove that this angle is the right angle, right? For that, it would suffice to actually prove that these angles give us what? Give us together the right angle. Well, but yeah, we can't do that like that because we would have to look at these angles, and well, we would have to use that this is okay. But maybe the other way around, like this is okay. We would have to somehow prove that those angles actually give us. Okay. Now look at those angles. And you see that they are standing on this circle like that, right? If you look at those angles precisely, then we'll see that they are standing on this circle, right? And for such angles, we could instead consider the angle that is just like that, but like that. And you see, this is just from the basically from how we define angles, that this angle, if we take this angle, this not, but I mean, if we take this angle, if we take now this angle and this is the middle point of the circle, then, and that we will discuss in detail, of course, because there are interesting things with that we want to look at. This angle is simply this part of the circle, right? That is true for unit circle. Of course, we like to go to the unit circle. So take the unit circle. Take the unit circle. And for the unit circle, we know something. We know, and we will return to this also in the subsequent considerations, but now let's look at that. For the unit circle, we know something remarkable, right? For the unit circle, we just know that the length is 2 pi r, right? The length of the circumference of the circle is 2 pi I. That is, if we 2 pi r, I mean, that is, if we would have taken this circle and we would have somehow taken a measurement tab, right? We would have rounded it around the circle, and then we would have exactly measured that, the tape, which we would just then put on something along its length, right? And we would measure that, then that would be exactly 2 pi. Well, of course, we couldn't measure exactly 2 pi for, I mean, for the circle with radius 1, it would be 2 pi. We couldn't measure exactly to pi, but the more precise our measurement is, the more precise we would get to pi. Wow. And now, now the thing is, that the angles, if we consider angles in the unit circle, we are just cutting out parts of the circle, right? Of the circle, if we consider this circle somehow to have degree measurement, I don't know, like 1 degree, 2 degrees, 3 degrees, and so on. They are cutting parts, they are cutting some parts of the circle. They're cutting them out. Right, and the thing is, the part, and I mean by the part, the segment, right? The part that it cuts out is, of course, in the same proportion to the whole circle. That is, if we take 360 degrees and we imagine degrees to be such segments with equal like elementary segment. Imagine we have an angle and we have these degrees drawn on the circle, something like that, right? Now just imagine an angle, and imagine that here we have 0 degrees, here we have 1 degree, then to this is 1 degree. Probably you have seen that picture. This is 1 degree, and this is part of the unit circle. This is a certain fixed part, and we go in these parts. Of course, that is supposed to be equal part, right? And we go in those parts, and we will count 360 in total, right? That could be angle alpha, and that angle alpha, I mean that angle, would then count, well, 0 degrees, 1 degree, 2 degrees, 3 degrees, right? And now the proportion of the measurement of this angle to the whole is here, of course, 360 degrees, is of course same as the proportion of the corresponding length here to the length of the whole circle, right? Right. And hence, we could just say, well, if it is like that, why don't we just identify this by setting this is our alpha, this is our L, and now we set, I mean, these proportions are equal, right? And now we set our angles, which we could also measure in length, right? Because we have that same amount, of the circle taken up by this length. If we go along this length, then this draws out an amount of the circle. And we have taken same amount from the whole circle as we have taken by the angle amount from the whole circle. So we have taken, I mean the proportion. So this in relation to the whole circle length, to the whole circle length, is just the same as this, what we cut out of the in 360 degrees divided area of the circle. This is in relation to the area, or we could also say this degree piece in relation to 360 degrees. These relations are the same, right? This is just visual, right? There we don't have any proof because this is just what we see, right? So that's about, again, things that we just take as it is. We just see that the relations are the same, just actually because it's a continuous process in which we enlarge one thing and the other thing. Yeah. We could also compute like the area of the sector and then have it precisely, but there in it again there are assumptions like this. So again, we have to take something for granted. All right, and now I wanted to explain you why this is exactly the measurement of this angle. Well, that is, let's call that alpha. I mean, not this alpha 3 degrees, but let's call it alpha 2. Okay. Why this angle is exactly this? Because what we'd like to measure this on the unit circle, we take explicitly the unit circle here. That was the general case, but here we have taken a unit circle. This is unit circle, this unit circle, this is unit circle. And we just say, let's measure those angular lengths, that is, those things that cut out angles in that they go on the circle. Let's measure them in that way that when we talk about such a piece, on the unit circle, when we talk about such a unit piece, at least on the unit circle, and those pieces are measured from the 0, and the 0 is exactly the point 1, 0 that we have already encountered, right? Let us measure this length in such units that this actually holds, because you see here I cheated a little bit. This is length, right? But length has not the same measurement unit as the angle, and so we are actually setting equal. Of course, mathematically it is okay, but mathematically it is okay when it is already something established, right? But here I just say that right? I just say that this length to the number is equal to this angle to the number. Mathematically, of course, numbers are all same. We don't pay attention to measurement units, but these things are qualitatively different things. And now we just say the unit of L is same as unit of alpha. You see, here we would have unit of L. Of course, it's complete and mathematical. We don't have units and so on. But let's just for a second imagine we had two different units, and so qualitatively um, for our visualization, it is kind of weird, right? That we set it equal, but we just say that we take this unit that what we imagine, so that this relation holds mathematically. You could also explain it without the units. It is just the proportion itself. We don't care. The proportion is certainly numbers, and the proportion just gives which part of the whole it makes, right? And these parts of the whole are equal, which means if we now play with it mathematically, the proportions are the same, which means that we can express alpha independence on L. But the important part is that this cutting out this angle now is identified with the angle measurement. So we can measure angles as lengths measured on the circumference of the unit circle. Okay. Important, that was on the unit circle. Right. Right. So we can kind of identify this angle with this length on the circumference, in that we put for the length exactly the right unit to allow for this identification. But of course, this unit thing is just a plausibility thing. We don't say what this unit is whatsoever. It is just to understand that this identification is actually a step, right? So this angle is equal to this. This is clear, of course, for the whole angle, 360 degrees. This is clear for 180 degrees. But this is clear because we identify it in that way. Because we say that this is actually same piece as this piece. Now, that's again for the unit circle. This is important that you understand that it is a thinking step. Of course, you could do it thoughtlessly. You could just say, well, this is this angle, done. But when you see a piece of a circle like this, and you say, that is this angle, why the heck would you do that? This is this angle. You see visually, yes, this is this angle, but what does it mean? This means that the only thing that matters is the relation, the proportion. Only thing that matters is the proportion. Because what is taking an angle? Taking an angle is taking a piece of 360 degrees. And what is taking a piece of the circumference of a circle? That is taking a piece of 2 pi. It is only important which part it makes of the whole. To measure angles, I mean. To take a measurement, if you make any measurement, you actually just say how many units. And the unit is in some proportion. And this is what is happening here. Right, okay. It was a very cloudy explanation because you can't really explain it properly, because they are just terms that they are just thoughts that that you can touch, but you cannot really catch. You can't catch it in words properly. Right, but now you know why we identify that. But this was for unit circle. What do you do for other circles? That's very simple. You have a unit circle, and this is your angle alpha. And now you draw a circle with any larger radius. And now you do that. This is the piece, and this is the angle. And important is this is the angle. So basically, you just enlarge that so that the relation keeps. But the relation, not the size somehow, but the relation to the circle, this angle to the circle, and then automatically, and this is the thing that is important, that is exactly what this says, and then automatically the relation of this piece of the circumference to the whole circle. Right. This equality of relations is actually what it means, that this piece of the circumference, as we look at it, as we compare it with other angles, when we take another angle of kind of same size, meaning we took same piece of the circumference. Oh, you can also see visually, but this is because of this relation. You have that visually because this relation persists. Because taking this means taking exactly the same piece. Right? This is why we can compare two angles, comparing their pieces of corresponding pieces of circumference of the circle. And this is what it means that we say that this is exactly the same goal. What does it mean exactly the same? That means it allows proper comparison with other angles. And it allows proper comparison with other angles because of that. You can contemplate it for a little. You don't need to understand it in clear thoughts because, as I said, this is things that people just say. They could give you one explanation, another explanation, third explanation. Everyone will give another explanation. If they are a good teacher, we will give at least some explanation. Well, not necessarily for that, but they will mention that. They will mention that at least, not necessarily in this context, but they will certainly mention that. Because this is really important. This identification, or this, probably they wouldn't call it identification, this relation is absolutely important. This is, by the way, measuring in pieces of circumference, as you know, is measuring in, this unit is called radian, is measuring in radian. Of course, we don't actually write this unit. We could, but we don't. And this is measuring in degrees. In degrees, you know that this is in radian. Radian, you probably also. Okay, so this angle is this because we think of that way and it works properly. That is why we keep this thinking. All right, but now we have to prove that this angle, and because of that relation, that actually properly works, that this angle is actually two of these angles, right? And now, of course, all relations are translated because of the size symmetry of the plane. So we can take any circle now, not only the unit circle, and we work now our way towards proving that this is actually 2 times this angle. Right. All right. I should draw a bit a picture, better picture. Mm. All right. Well, let's say that is our circle. That is our angle of each other. This is the middle point, middle point of the circle, of course. And we have to prove that this is 2 times this, right? All right. Well, let's see. How do we prove this? And actually, it doesn't depend if this point is here or maybe let's draw it very generally. We don't need it in this generality, actually. Maybe we will just stick to this case. But, well, let's draw it generally because it doesn't have to be like this. It can also be somehow. Okay, this is a little bit, but this can be like this point could be anywhere such that we would have this. Okay, I'm drawing nice cases actually. I'm drawing cases where those triangles properly give it, but let's because it doesn't matter. Wherever we take this point, it works. Right, this angle would be always 2 times. Actually, it's 3. 1/2. I'm keeping saying 2 times. Of course, 1/2 because the angle of the target angle is supposed to be 90. So this should be 1/2 of this, right? This angle should be 1/2 of this. And we see that it is, sorry. Right. So we have that just by our relation identification or proportion identification, and we need that. All right, let's see what we can do. We need to show 2 times this, right? Well, maybe let's consider first a simple case. It is, of course, not necessarily always this case, but let's consider the simple case. Well, this is free ready, right? And so these triangles actually have two sides, right? So the simple case is that we have that, and we have that middle point, and we sorry, simple case. Hi. Why the heck can't I draw a proper line? So right. Okay, this is ready, and this is three triangles, right? And well, I have drawn it now to be exactly on the. It is supposed to be drawn. It is supposed to be drawn so that this is exactly the. But do I have to do this like that? Oh no, let's just draw it so that we don't have here intersection of those lines, right? This line is probably this does not intersect this line within this row, right? So this line does not intersect this line within this row. This line does not intersect this line within this row. Then we can always do this radius trick. All right. All right. Then of course, all three triangles have have two sides that are equal respectively. Right. And well, now try to do something with that. Mm, oh, if first angles would be equal, let's do that also. All right. Wow. What do we have here? We don't have that. All right. If this triangles are equal. Okay. So the more simple case is even simpler. We cannot, it is not just that we can draw the radii, it is that these triangles are exactly equal, right? This is with symmetry, drawn with symmetry, right? Those triangles are exactly equal. And with that, we just have that those angles are equal anyway, right? Those angles are equal anyway because it is triangles of this kind, right? Right, it is two these triangles like that. And you have equality there because the equality of the angles there, because you could draw the height, right? And the height would be the common one, right? Okay, we wouldn't know yet that this is right angle. Would we not? Wait, what did we want to prove? We know that this is right angle. Okay, we have to prove that it is a right angle. Right. No. I want you to actually use that it is right angle. Wait. Yes, I wanted to use that, but actually I wanted to use other thing. I wanted to use that it divides this triangle into equal triangles, right? And for that, that we can draw. I wanted to prove that we can draw a line that divides this line into two, and then by construction, those two triangles are equal, and then those two angles are equal, right? Right. Why do we have that? If we have those two sides equal, right. The thing is, if we have those two sides equal to each other, then there is, it's just, you could say it is an axiom. It's not quite, but if you have just two lines intersecting somehow, then you actually have, if you take those rays, then you can draw a line that divides those two angles. That divides this angle into two equal angles. This is just symmetry. If you would draw lines like this, then this angle together, or these angles together, they give this big angle, right? And this doesn't change, and this angle changes a little, a little, a little, a little, and this on the contrary, this angle gets, if you rotate this line, and this angle grows, this gets smaller, 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 and then at some point you could just consider, if you recall from analysis, like from calculus, I mean, you could consider those are continuous functions, of course, and you could consider this okay, you could consider this. This is alpha, this is beta. And you would know, since beta is a function of alpha, and alpha is changing continuously, then you would know this is a function of alpha, right, on some interval, on some closed interval. This is a continuous function, and then you have alpha minus beta alpha. And well, here you then have, you just start, okay, let me do it properly. The argument, you see, you could consider this angle alpha, and you could call it alpha, you could call this angle beta, all right, and you would rotate this line, thus changing alpha and changing beta, where they don't change independently, but the change in alpha already determines the change in beta, which means if we take now some alpha here, that is smaller than beta. We just take an alpha smaller than beta and we start to rotate this line, right? Then beta is just, well, actually we could really easily say that is that let's say that's gamma. Alpha plus gamma minus alpha. Yeah, I just didn't care what it is, okay? So gamma is a constant, alpha is an angle, and then we have a continuous function that is given by 2 alpha minus gamma, right? 2 alpha minus gamma, and this starts somewhere negative because we have taken this beta, this is actually beta, to be bigger than alpha, and this goes, this is alpha start, and alpha finish will be something positive because we will go to here, right? So alpha finish will be positive, this is negative, strictly negative, I mean. And this will be alpha finish minus gamma minus alpha finish will be something that is bigger than 0, and then we can just start, consider this function on this interval, alpha start, alpha finish, and then we would get a 0 of this function, and so there is a line dividing those that angle into angles, right? This is just continuity argument. Of course, we would have to justify that this is a continuous motion, but this is just what we know from visual things, right? So they just take it from visual. This is again an axiom that such motions are actually continuous. Continuous in the sense that we can regard them by the means of calculus and use such things, right? I don't remember what this theorem is called, intermediate value theorem, but it's just that a continuous function that goes in an interval and takes somewhere A and somewhere takes B, it has to take C because just it is continuous, so it doesn't have holes, so to speak. So it has to take C somewhere. Right. This is this theorem. I think intermediate value theorem, but I don't know exactly. So there's a line dissecting this angle into 2 equal angles. These two are equal. Okay, and then we don't need that. We could prove that too, but we don't need that. Okay, we need that. No, we don't need that. We don't need that because visually, just again, visually we accept this construction, this line drawn like here, and we have drawn this line between this point and this side. We can do that because we can connect this point with the side, and we can do that without intersecting other sides because we can do that inside here. And we know that this will lie inside because we have just visually seen that this happens here before it reaches beyond beta, right? And so indeed, this is a valid construction, and then those angles for such constructed line, they are equal, and this is equal, and those angles are equal, and this side we share. So those triangles are equal, and those triangles are equal, and then those angles are equal. So indeed, in such a triangle, those two angles are equal. Alrighty. Then we look at this here. This most simple case, right? You remember. We look at this here and we just recall that, yeah, okay. You have just to solve an equation system of sorts. This is some alpha. Okay, those triangles are probably even equal if I recall. Oh, okay, of course they are equal because we have constructed that now to be symmetric, so they are equal. And this is just some angle alpha, this is alpha, this is alpha, this is alpha, and this is some angle beta, right? And now you just have 180 minus 2 alpha is equal beta, and you have 180 minus 2 beta is equal, I don't know, 2 points. That is 2 points. The equal the angle gamma. And well, this is 2 radius, so this angles are equal, and 180 minus gamma. Wait, we wanted gamma, so we don't need to go far. We just have that. Okay, we need that. Okay. Gamma 180 minus gamma. I mean, I use the sum in the triangle. We'll prove it in a minute, in a second. 180 minus gamma is equal to 180 minus alpha. Not 180, but okay, I need that again. 280 minus 2 alpha, right? These two angles of this triangle. I mean, I take this big triangle and I consider 180 minus 2 alpha to get those two angles, right? Then I can take those two angles and I get that. So I get that cancels, and I get actually, okay, that was much easier. We already get the result from here. Right, it works because 180 for this big triangle, right? And then I take this two alphas out, 180 minus 2 alpha, right? And then, okay, it's much simpler. It's just 180 minus 2 alpha. Okay, wait a minute. That's already those two angles. This is already those two angles, right? Okay, it's simpler, but not like I thought. We take 180 minus 2 alpha, and I mean by 2 alpha this. And this is equal to 2 those angles we don't know. All right. And 80 minus 2 alpha divided by 2, right? This is this angles, right? Divided by 2 minus alpha. Because I take this away and I take those, I get those angles, right? So what I did now, I took this big triangle, the sum of all triangles in this big triangle, the sum of all angles is 180, right? Now I subtract this angle from that to get those two angles, those two big angles, right? And then I divide by 2 to get one such angle, and then I subtract alpha to get this angle, right? And then, of course, I take those angles, and 180 minus this, minus 2 those angles, should be gamma, right? I just computed this, taken this angle, 2, and I subtracted them from 180 in this triangle, in which gamma also lies, right? And I got gamma from that. What is that? Well, this 2 cancels, and we get also only this plus 2 alpha, and this cancelled, so 1 minus 180 plus 2 alpha. All right, and that gives a funny result. Okay, this 2 cancelled here, sorry. This is, of course, just not plus 2 alpha, but just plus alpha, right? But then 3 alpha. Okay, don't think that I'm doing some funny stuff here. I just computed it fast and I missed some things, right? 180. Then this fraction here, 2 goes away and 2 goes to here from this, right? So this 2 goes away here, and minus comes to here, and we get my 180 minus 180 and we get plus 2 alpha. Plus 2 alpha. No, we don't get plus 2 alpha. Instead, we get, since that is, okay, that is eliminated, that is exactly plus 2 alpha. Okay, plus 2 alpha. Right, but then we get that, and we get plus 2 alpha again. Okay, I don't like that, because now gamma is 4 alpha. Right. Okay, gamma is 4 alpha. But this angle here was 2 alpha, and hence gamma is 2 to alpha, as we liked, because we wanted to show that this gamma is 2 times this angle, and if this angle is 2 alpha, and gamma 4 alpha is exactly what we wanted. Okay, this was for nothing. Okay, let's a quick proof that we have 180 degrees of angles in triangle. That's just alpha, beta, gamma, and this is alpha, and sorry, because that's wrong way around. This is beta, because we have that as that angle, and that is a parallel line, right? And we can draw parallel line by the parallel postulate through this point parallel to this line, right? This is beta, and this alpha, this is alpha. And that this for angles at parallel lines works, well, this is actually just how it works. We just see it visually. So this is an axiom actually. Angles at parallel lines are an axiom. Right. Because we have to start somewhere. If we don't even have the sum of angles in a triangle equal to 180 degrees, well, you're screwed. Right. Okay, I just now realized that we probably, well, we could continue proof, of course. I mean, one case we already have, symmetric case. The next case would be case where we still don't cross the line, so the point is here, and we are not symmetric, but we do not cross this angle, so this is again proper triangles. But I guess I realized that we can immediately proceed with our proof, because if we have something like that, okay, maybe we cannot. If we have something like that, we have this radii, right? And on the other hand, we have that. All right, that is orthogonal. Well, sorry, that's a really bad picture. Okay, that's not better. Yeah, something like this. Okay, then we have our diameter, and then we have our triangle, right? Then we can draw from here our radius, right? And this would actually give us two triangles. Where this is, this angle is equal, this angle is equal, this angle is equal, this angle is equal. And now, well, the point is, this is not necessarily that. Wait. Okay. Then we could draw a tangent line. We could always do it, right? Would this always be? Yes, that would always go to this point, right? And I mean, it does not depend on the picture that we would have that this is that this gives exactly those relationships, right? And now we would have that angle, that angle. We would also have that angle, that angle. And we would be interested in that angle. And this is the sum of those angles, right? This is also the sum of those angles. And those angles give 180. Uh-huh. So, okay. I think there's a much simpler proof than arguing with those things. Uh, I I could continue with that, but I don't think I need to. You see, if you call that alpha, we prove that if the sides are equal, then the angles are equal, so that works. Beta, gamma, and this is, I don't know, omega. Then you just see that your omega plus your gamma is 180, right? This is just this angle, and that this gives that this is just by our thing that we measure angles as something measured in something, and then those parts are exactly the parts that give this part, right? So the sum, and we want the angles to behave properly. This is an axiom, and then the sum of those parts is exactly that part. The sum of those angles is exactly this angle. Right. All right. And then we have 2 alpha. 2 alpha minus omega is equal 180. I'm just in this triangle, right? And then we have what do I say? 2 alpha plus 180. But I didn't want that. I wanted 2 alpha to be 180 uh, minus omega, and now we have 2 beta is equal 180 minus gamma, and you see what happens if we use this and we add up those two equations. Then we get that 2 alpha plus beta, where alpha plus beta is exactly the angle we'd like to be 90 degrees. This tangent is actually not necessary. It's much simpler than I thought, actually. And that is equal to 260. And here we subtract exactly the sum, and this is 180. And then we divide by 2. So this is 180, right? 360 minus 180, where we subtracted that sum, and this is alpha plus beta is equal 90 as we liked, right? So this was really simple. All right, now we'd like to prove the Pythagorean theorem, right? Okay, first observe that any triangle, any right angled triangle can be indeed put into a circle, where the circle will have exactly, of course, the diameter of okay. How do we know that? Well, it's just about figures we can inscribe in a circle, we complete our triangle to a rectangle, and that we can inscribe rectangle in the circle. Well, we could just say that we do it by a compass, or we could prove that, and proving that, well, if I recall, this is not trivial at all. There you have to use limiting arguments, so you can't just prove that something can be inscribed in a circle. Oh yeah, it's kind of plausible that you can, because you actually would have to prove that it really works, that only the points lie on the circle for some figure, and the figure is already in the circle. So yeah, we'll take it for granted. There are some proofs for that, what figures you can inscribe in a circle. Well, to show that a rectangle can be inscribed in a circle, we just take 4 points such that actually, again, we use the symmetry of whatever of R2 of the plane. And you see here we just take what is a rectangle. We take a pair of points with equal distance. We take another we take 2 pairs of points with equal distance. Right? We just took those 2 pairs. Then there are unique lines for those 2 points, respectively. When we took those points, we rotate that to be parallel, right? Then those points are somehow like this, but they are parallel. They have still same distance. And then we slide this line until the closer point, they are parallel, so there is closer and less close point. The closer point, we slide this line so that the point that is closer to that point. No, that is on the right, on the left of this point. Let's call it like that. That is on the left of this point. Okay. Well, okay. Let's just consider it visually. I don't want to describe it because there are some subtleties. We would, of course, I could give a precise description, but let's not be caught up with that. We just slide it until we get the rectangle, meaning that the distances. Okay, we just slide those points until not only those distances are equal, which is given, but also those distances are equal. And then we slide more so that the angles are right angles. And this is a rectangle. All right. So rectangle is given by such points, for which it is true that these points have same distance, these points have same distance. So all pairs of points, and the right angle is given here, and right angle is given everywhere, but there is one right angle that suffices, because if you have points that already satisfy all other things, right? This distance is equal, this distance is equal, this distance is equal, this distance is equal. In other words, the line segments between the points are always equal if you take the disjunct pairs of points, that is, the pairs of points that share the points, and the line segments of such lines will be always equal. That is parallelogram, right? And then you slide it so that you get a right angle, right? And you have to give a circle. You have to give a circle so that the circle is really outside and all points lie. Of course, that would be the central point of a circle, but how do we show that it really works? Well, you could show it by compass, as I said, but we could show also okay, I wouldn't know a proper proof of that. It's like I don't know what we are allowed to assume and what we have to prove actually, because it's like you have to formulate precisely what you have to prove in this case, because visually it's clear. You just have to prove that you can draw such a circle, but actually what you have to prove, what is a figure inscribed in a circle, it's not that easy to describe if you think about it. It's just that we go the other way around. Oh well, we can't go the other way around. Okay. For any 3 points in the plane, there is a circle. For any 3 non-collinear points on a plane, this is circle for them, right? And then if we take a rectangle, then the question is if that circle actually takes the 4th point. Okay. Since this circle goes through those 3 points, we know that these 2 are on the circle and this point is on the circle, right? And mm, well, any 3 points. Determine a unique circle, right? Or is it unique? To show this, you just have to solve the system of equations. I don't do that. It's, yeah, you have to solve system of equations that actually describes circle going through the 3 points. So you take the general form of circle and you have to show that for any plugged in non-collinear points, you have to account for the condition of non-collinearity, and you plug in those points and you got like 3 equations, and like equations will be something like quadratic in form of first square root, and you get quadratic equations. And what you will get then will be the 2 equations will wait, you will get a radius and 2 middle point coordinates, and the thing now is we'd like to prove that this point also lies on this circle. And this equation also will give you the uniqueness. The circle or the solution will be unique for those 3 points. Right, for non-collinear points, here's exactly one circle that goes through them. Alright, or we could take it as an axiom that 3 points define a unique circle. 3 non-collinear points define a unique circle. Alright, and then the thing is to show that it actually goes through the 4th point. I mean, this is for inscribing a rectangle, right? And the idea is if you have for such a figure 2 points that are on different sides of the 3rd point, then the circle going through them would necessarily have the line segment connecting those 2 points as the diameter. But why? How could I show you that? Well, it is actually that's not true. That's not true. We could have something like this, and the circle would be like this. So that's not true at all. Sorry about that. But well, let's see. Now you see here you have equal distances as you have here. And okay. Just by circle symmetry, this piece between those 2 points of the plane, this point lies on the circle, it doesn't lie, doesn't matter. You see from here, since you just have that piece of a circle, would that be true if you have that piece of a circle here? Yes, that actually would be true. If you have that piece of a circle, right? And you have that point that is kind of in the same way from those 2 points. And of course, you have to continue to go like this. Okay. Okay. Oh, but the circle doesn't have to be symmetric along any line that you draw, right? No, it does not, but you see the distance, if we take those 2 points that lie in the circle, the distance of this point and of this point from this point, oh, but this also be true, but also be true for this. Okay, I'm a little bit confused. Actually, there's another news. I don't need this. I don't need this for my considerations now, because through any three non-collinear points there is a circle. So any right angle triangle can be inscribed in a circle. All right, this is an interesting problem, but not for now. Okay, so we get that, and with that we get that. So yes, we finally got it, that any right angled triangle can be described in a circle, and probably we even didn't need that actually, because we needed that to construct our right angled triangle. But now a right angled triangle can be just inscribed in a circle, and then we can try to prove the Pythagoras theorem, right? All right, why did I actually need this circle? Um, hmm, I don't know it anymore. Hmm, the idea was that I'm not satisfied with geometric proofs of Pythagoras theorem. I like to have a proof that really proves it, starting by the axioms, right? But for that, I need some kind of relations, right? Otherwise, I just don't have um, the possibility to work with it. Well, let's just derive some kind of relations. I don't know, something like that. Right. We have a triangle here. Okay. I see. You know that we can construct a perpendicular from a point to a line. This is by the way, again, I believe equivalent to parallel postulate. So it's again this, right? Um, and if we have right angled triangle, then two right angled triangles rise again. Okay, I believe I know how. Um, this is one angle of this right angle triangle, right? And we have ABC. And those are actually, if you look at that carefully, that shares ABC and ABD share two angles, and that makes them similar triangles, right? And this triangle and this triangle share an angle, and this makes them similar triangles, right? So, not knowing the Pythagoras theorem, we get for that matter that that those triangles are similar to same big triangle ABC, right? So they're similar to each other. And wow, Of course, like hypotenuses, legs are similar to legs, and hypotenuse are similar to hypotenuses. All right. The question is if we can somehow. Oh, wait. I see something. This is similar to this, and this is similar to this. So there are some coefficients by which AB multiplied by K is actually equal AC, but now look at AB, that is A. Right, so we have AK is equal C because that is equal C, and we have AK, and here we have this triangle equivalent to this triangle, and well, I mean similar. This triangle is similar to this triangle, and this is the hypotenuse. This is A, this is B, this is legs. This is B, and this is B. Sum L is equal C. And now we are interested in the relation of K and L. Because that might really give us something. Let's see. What is K and L? Let us see. The thing is, it's somehow this is related to this. I mean, this is related to this as, and we also have that, right? We have that. Let us square it for a second. Because if you would have that k squared plus l squared is equal 1, then we would have done it. But why are they equal 1? Okay, well. You see, those are similar themselves. That is, A and B also have a coefficient, right? Because they are similar to same triangle, right? They are similar to same triangle, so they are similar themselves. And A is equal as B. What does that mean? Well, we are interested in those, right? We're interested in k squared plus l squared. Well, k squared. Okay, I should be careful by dividing things because okay, no, everything is non-zero, no problem. K squared L squared is, well, well, I know I don't want to do that. I'd like to do that rather. C squared A squared B squared. I also recognize inverse cosine or sine depending on the angle. That is L squared C squared B squared. And you see, now we can replace that A by SB, that is C squared A squared B squared, which gives us, well, C squared B squared K squared. This gives us S2 K2 equal L2 squared. Well, that is not that reassuring. because, well, well, but this is one relation, right? And we could replace that by that, obtaining. Actually, that can't be true, right? Ah, okay. Well, no, that's nonsense. Well, I don't like that. You see, have to show and you see that is k squared, that is l squared, 1 plus squared equal 1. That is, no, 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 what? No, 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 have to show them. Okay, let's go, so to speak, backwards. A squared multiplied by k squared is equal 1. That we have to show, or that we have to show so as we like, but best we show this. And you see, of course, you recognize that this kind of cos and sine, well, inverse cos and sine. Is that even true? Well, depending on the coefficients, okay. K plus, actually, that would be funny, right? If you would have that, and you would have that. I mean, of the same angle, of course. So something is wrong. This should work, but it does not. Sorry. What am I thinking? I couldn't. Oh God, I'm really stupid. Like that mistake you should be able to do. Like, yeah. Okay. No, God. What am I thinking? What am I doing? Okay, maybe it has been too long, but okay. But this is really stupid. I mean, ah, I can't have it like that because, of course, what I wanted wouldn't work. What am I thinking? Okay, from that we don't actually get it. But what is important? A is equal as right, and of course we wouldn't want to have that relation that I thought of. That was very stupid. Okay, but we have SBK is equal C and BL is equal C. And as you recall, those okay, S is here coefficient and the coefficient, and from that we actually get something interesting. We get that SKL is equal 1, right? Just divided both things by each other, and that gives us that is K is equal L. What the heck does that mean? S was the coefficient of similarity between those two triangles. And K was the coefficient by similarity of one of those triangles with the big triangle ABC, and L was the other coefficient, right? So what that means is actually that if we take of one of those triangles, okay, it doesn't matter. I do not distinguish that because it doesn't matter which is which. We just have to keep it constant, right? Which is which. And so AK, and because those coefficients could be inverted, so it doesn't matter for now. But now BSK is equal BL is actually equal A. Does it give us something? No, I'm somehow missing the one. I'm missing the one. Well, let's consider C. That big thing is C. I'd like to have this plus this, right? Maybe this is A squared and this is B squared. Well, maybe this is equal to A squared and B squared. Who knows? Let's look at that. C is equal to, or maybe whoa, maybe it's not. Of course, it is not, because we could take large enough, and then that A squared would be bigger than that. Is, well, of course, wouldn't make that would be bigger than that. Wouldn't make sense, right? But maybe it is equal A squared plus B squared. Okay. Let's think about how we could do that. And the answer is that this is actually proportional to this, because it can't be that those two are, okay, no, this is proportional to this, and this is proportional to this in this triangle, right? Those two are not proportional, but this is same, right? And this is same, let's call it H. And this is proportional to this in this triangle, because those two can't be proportional. Their ratio is not 1 of those triangles in general. I mean, the ratio of their sides, but okay, I call it ratio of triangles because, yeah, also of angles and so. No, of angles is 1, but of their sides, exactly. So this is proportional to h, and this is proportional to h. And h is the height, whatever it might be. But this piece, well, let's call it, I don't know, D. This is E. And D and E are proportional to H with what constants? Well, one constant of those is the inverse of the other constant, right? Because of those triangles are proportional to each other with inverse constants, because this triangle is proportional to this with this constant, this with the inverse of this constant to this, right? And this constant we call m or whatever, dm plus e 1 divided by m is equals c, right? Actually, I should not call it m. I should call it, well, a proportional to b, then a would be that. That should be s, right? Wait, I have to be careful. Yes, that is s. That is s. Because we have to, no, that is to compute a, so that is to compute d with respect to h, right? Exactly. That is D is that, sorry, what am I doing? We have the known sides, and we'd like to compute this D plus E, right? And we have that H, and we have now this D in this triangle, so it's like S. And here we have E, which is H multiplied by 1 divided by S, right? And well, the problem is now H is again nothing connected to A and B. Oh yeah, so oh well. Okay. The big triangle has the area AB divided by 2, right? And this is same area as C multiplied by H divided by 2. The proof for the area of the triangle, well, generally the area proofs, you can't just, you cannot just give them in any way. Oh, okay, you can. There is some limiting argument, but of course, it is, of course, again, based on assumptions. So the thing that I can suggest you, uh, I don't know. You know that functions like this are integrable. So because it is continuous, so we can use the Riemann integral, right? And you just know that each triangle, again, that's visual, so it's kind of an axiom. You can draw each triangle like this, so it's pieces of two lines, and then you can integrate that. I won't do that because it's just integration of a line. And you know that the area of a triangle comes out, so you can integrate that. Of course, don't forget to take the absolute value. And then you can look at what comes out there. Oh, okay, we have to connect it to the height somehow, and to the ground line. Yeah, okay, that wouldn't work well. Okay, the ground line you get again by sine. Okay, no, we can't use that yet. Okay, okay, we can't use that yet. So the area of the triangle to relate the height to the ground side. Okay. The thing is, for that triangle, it's just half of the rectangle. For the right-angled triangle, it's easy. It's half of the rectangle. And that for rectangle, we have that. That, yes, that we prove our integration, okay? Right. Of course, again, we have assumptions. We have assumptions that integral works, that it really gives the area under the line. So in calculus, here are lots of assumptions that are simply completely taken for granted, but it is like it is, right? So for such triangle, we get that. I actually also for parallelogram, because for I don't know what it's called. I call it parallelogram. Because yeah, you get same thing basically. Right. Um, Same thing but tilted. Or you could compute such. Okay, you could compute that for parallelogram. Having for right angled triangle, you could compute that like that. So you get it for any triangle, because half of the triangle is just that. Yeah, it's just that, right? Okay, you don't get that. You do not get that exactly. Okay. So you would have to prove additionally that you could compute the. No, you couldn't. Yes, you could. No, you couldn't because parallelogram doesn't have that. Wow. Yeah. So there would be some things to prove for general triangle, but we don't need it for general triangle. We only need it for right angle triangles. So we have that. Right. And now we get that. And we get that relation. Can we do something with that? Let's see. We also get that a squared, a is equal as b. So you recall this here is just okay. What is a medium? Yeah, that is one computation of the area of our big triangle, and that is the other computation of area of our big triangle. That all works perfectly. A divided by b divided by 2, h multiplied by c divided by 2. And we have just checked that for right angle triangle we can derive the area formula by integration. No problem with that. And what we get here is in CH is equal AB. This is of course not yet what we wanted, but we are close because A is equal as B. And that is finally something squared, CH here. So that is SB squared. And SA squared, wow, same way, CH is equal to 1S squared. And this gives that, yes! Finally! I mean, that we have derived same ways here. Actually, we can bring it to the other side, right? So in we replace one time this, and we replace one time that, and we get that, right? So, and we had that relationship. So that relationship is what saves us and gives us the Pythagoras theorem. Wow, what a ride! I didn't think that it is that kind of. Oh wait, no, it does not. It does not, because we have actually see. Okay, okay, I'm not getting that right now. What? Okay, that's yes, 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 yes. SB squared plus 1SA squared is equals C H. Okay, no, 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 no. Okay, no, you don't get that. But we were so close. I thought so. Okay. We don't get it yet. Okay. Ha. Ha ha. Wait, something is. No, it's definitely that. So the weird thing is. Wait. I should pay attention to what I'm writing. It's 2CH. Right? And now 2CH. 2CH is equal. That is C divided by H. Okay, and if you multiply that by H, we get exactly that, right? Okay, let's multiply it by H. and then we get that. We can't. Okay, I'm making the same mistake. We can't actually do that. We cannot do that, but we are already so close, so it seemed like that to me. No, 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 no. Our ride is not yet over. Haha. Okay, well. Ah, okay. I don't see yet how to prove this. Something is missing. CH is equal S b squared. B squared is equal D squared is equal CH. Right. Maybe we have that, but I didn't see that properly. Well, certainly we have something similar here. Right. What we have here implies. Okay, I have seen that without having seen that. It's just, I knew it works, but I didn't realize how. But now, this is just derived from here, right? This is derived from here, this is derived from here. And now we have, because this is here, this is here, a squared plus b squared is equal c squared. All right, what a right. We have proven Pythagoras theorem. Proof of Pythagoras theorem finished. All right. So, again, how did we do that? You see, we actually needed only two relations. We needed that. Those were the respective coefficients. Maybe not just two relations. So we said that this triangle ADB is similar to that in that sense that for S is chosen as the proportion coefficient in the direction, so that the sides of this triangle, the corresponding sides at the hypothenuses of two right angled triangles are of course the corresponding sides, right, in front of the right angle, right, are computed like this side is S multiplied by the side of this triangle. And we had this relation from that. Right. And then we arrived at that because we could draw the height of our triangle to the side, and we have reflected on how the height can be drawn just by parallel postulate, basically, right? And then this height was of course similar to this side, as side of this triangle. This height was similar to this side, and that those sides will be sides in relation. And that is given, of course, because those two triangles are similar, and it can't be that they have ratio 1, because we would draw different rectangle triangles, right? So, and they would be always equal if ratio would be 1, right? Right. So this is this side, and this gives in just according to this formula. This gives d h multiplied by s, because this relates to this side, this relates to this side, right? h multiplied by s, and here the coefficient is of course the coefficient of now this side compared to this side of this triangle, right? This side of this triangle compared to this side of this triangle gives you that, right? And here we just had area considerations. A very simple area considerations. We can compute the area of our triangle in two ways, right? All right. We can compute it by the legs, AB divided by 2. We have also proved that it goes, and we can prove it, we can compute it as CH divided by 2. All right. I now realize that I didn't prove that we can actually also compute for right angle triangle that that this is equal to this. Well, the thing is, yeah, we have actually to prove that this is equal to this, that this product is equal to this product for right angle triangle. But we could just use that relationship, because if we have A is equal SB, then we just have that A multiplied by B is equal to SB squared, and this C multiplied by H is thus H squared S plus H squared 1 divided by S. And now we have like this AB, and we have that, and we'd like to prove that this is equal to this, right? And we can't use Pythagorean theorem because we use the computation of the area of this triangle to prove it, right? So we have to prove it first. Right. But you see exactly here that we have that. Okay, I know. Here I used that. Okay, here I already used that. We have to prove that this is equal to S squared. Well, okay, that will be equivalent to proving H squared S squared plus H squared is equal S squared B squared. Alright, and we have to prove that this is actually equivalent to this, right? And this is H squared plus 1. Okay, no, it's not getting us anywhere. It's maybe a bit contrary. Okay, you see H was related to A and to B, right? So C was related to A and to B. C was related to H, and H was related to A and to B. And how was it? Was it? No, it wasn't. It was in a certain way. It was in the way that H. Okay. You see, A by B, A multiplied by B is same as SB squared, or same as one is a squared and it is of course same pieces. But we can't use Pythagorean theorem right now. Okay. That was nonsense. Yeah, the question is, why does it actually work? At least in right angle triangle. And then actually we can derive for triangles this formula from the area of right angle triangles. I'm pretty certain. Okay, now you see we'd like to have those. Yeah, the problem is AB is disconnected from that, but not quite. B has no connection to H seemingly. Yeah, I don't think we can prove it that easily like that. I think after either of the things we have to assume either the Pythagorean theorem or the computation of the area of the triangle. So we have to assume one because there is no connection. There's no proper connection. H is completely disconnected from A and B. The only way to connect is A, B. And A couldn't be. Well, it's just we remember that S is the coefficient of A to B. And here we could plug it in. It's weird. And divided by B. And here it's squared. That actually okay. And that is bringing them in at least. Oh, you see, we have that. Okay. Let's try to replace that by the wish to. Maybe replaced by that, which is that is now A divided by B. Let's see, sorry, SP squared we like to show that okay, that we have, and we'd like to relate it to sp squared. Wow. But this gives some interesting stuff, right? Or we could also replace it by sp squared, but let's not do that. Instead, a squared plus, no, let's do identity. Oh, nice. Okay, of course, we're starting here. We want here. Okay, yes, of course. We really can't create any connection here. Yeah. No. We don't need it. We don't need it because h multiplied by c is just another way to compute in these triangles, but to compute exactly by the formula that we can prove by integration. So h c2 is equal exactly to dh2 plus EH2. So we have that, and with that we have the Pythagorean theorem completely proved. Right. Alright. That was already a lot. And we have started some things and didn't finish some things. Right. Yeah. What I actually wanted. First, this proves see. So you see here we add something, and the square root is monotone, so we just have that basis. This is bigger or equal, because the square root is monotone. Bigger or equal e squared. And is now positive, right? Because we just have sides of a triangle. And that is bigger or equal a and b. Right. And with that we have that indeed. Alright. That for triangle doesn't make much sense, but for triangle we just have this and this we have automatically, because those quotients are of course bigger than 0 for sides of a triangle. Right, we don't have negative sides. Alright, now I don't know where I should write it best. Actually, here. So you see, we have that triangle ABC with its sides, and we have those numbers assigned to the angle, sinus, cosinus, and also for such beta. Now you see that for beta, everything just reverts. So we can note, since for beta it reverts, and beta is just beta is just 90 by sum of the angles in the triangle. Beta is just 90 minus alpha because 90 is already subtracted. So we note sine of 90 minus alpha is equal what? Well, for beta, the side on which the angle is this, and so this is just b divided by c. It's actually cosine of beta, right? We have defined the side, for which the cosine is the quotient to the hypotenuse, and which the angle lies, right? So that's exactly cosine of, and the other way around, the sine of this would be this our side a divided by c, and this is cosine alpha. So we have proved that in a triangle, right? This is a known trigonometric formula, and we haven't actually proved that, but it is too simple to really prove, because this is just what we see geometrically. Right, this is just how the triangle works. Alright, this is in a triangle, in a right angled. Right angled. Okay. Okay, this is in the right angle triangle, and we can memorize this formula. Well, better we do not memorize that, but we understand this relationship and can simply recapitulate that in our mind whenever we like. Right. And tangent of alpha, and I only do it for alpha because for beta it's like obvious, right? But pay attention. Similar trigonometric identities, of course, you can do also for a tangent here, right? And you have to think how it works here, right? Okay, tangent alpha is just sinus beta, sinus alpha divided by cosinus alpha, which is of course nothing else than, well, sinus we had here b above, right? And here we had a, where b was the more remote side from alpha, right? B divided by a, AC, AC, b divided by a. Alright, that is tangent alpha. And cotangent alpha is of course divided as 1 divided by tangent alpha, which is nothing else than, and this all occur in definitions, right? I could do it like that, could do it for cotangent like that, could do it for cotangent like that. When the triangle angle is specified, it's all occur in definition. Right. obviously, actually. Right. This is in a triangle, right? This is a triangle, but we know here, actually, this is in a right angle triangle, not in a triangle. This is in a right angle triangle. But right angled triangle is boring, right? It gives us only a small piece of what is possible. We could have very large angles, and we'd like to have their sine, cosine, and so. And a very important object that plays a role in extension of the trigonometric functions of angles and to our angles is the unit circle. This is one way to view it. Meet again. The unit circle. All right. Well, let's do it more properly. The unit circle, as we have already had in our proof for the tangent line being orthogonal to the radius, we considered only that special case, which was allowed for symmetry. The unit circle is a circle with radius 1. Alright, and I already drew it in coordinate system. This is the point 1, 0, 1 in x coordinate, 0 in y coordinate. This point will indeed play a very important role. Right, you see, on such circle we could have very different angles. Right, this is some angle, this is some angle, but also this is some angle, and so on. Right. Now we like to extend the notions of sinus and cosines. How do we do that? And of course, our trigonometric functions too. Well, we do it very simply. We just observe the following. This is the unit circle, right? The unit circle means exactly that this radius is equal 1. Just what we used in the computation of the area of the circle, where we looked at the proportion angles to lengths on the circle, right? This is one. And now just observe what happens when, and you see, this is one. And this defines a right angle triangle simply by means of a perpendicular brought down onto the x-axis, right? When this angle here is some angle alpha, and that is more than 90 degrees, that will always define such a triangle. And this is radius always equal to 1, right? And this will define right angle triangle. Now observe what happens when the hypotenuse in a right angle triangle is actually equal to 1. You remember, the quotient is always to give hypotenuse for by sinus and cosines, right? So sinus alpha, and that is, let's call that B, A, let's call that B, just to have same notation. This is simply B itself. This is the length. This sine is the length of the side mode from the angle. This happens
when this is 1. And this is not a miracle, this is just how we define a sinus as the number assigned to such an angle for a given triangle, and it turns out that for such triangle, well, the measurement of the hypotenuse is 1. Oh, this is just that, right? But geometrically, or visually, it is convenient. You'll see in a minute. Alright, and this is just a same way, right? And what you see here, you see then that it so happens when we have such a triangle that this, exactly according to this, right? This is sine alpha, and this here is cosine alpha. So for an angle, and that was now alpha smaller, let's not take small and equal, because as you see here we have a problem with our triangle. The triangle actually becomes degenerate. There is no third side, so to speak, only two sides. Wait, yes, exactly, because that's the radius, right? And the hypotenuse is same as the leg, right? So here alpha smaller than 90 degrees. All right. And you also see, if you recall, that we are in a coordinate system, that this is just y coordinate of this point. This is point with coordinates, of course, cosine alpha, because this is x coordinate. So for unit circle, we have very conveniently the connection of the coordinates of points with the trigonometric functions, and this is an intrinsic connection that simply relates, or that simply arises from our definitions of coordinate system and of how we define sinus and cosines. That is like the interplay. We have defined them, and since we have defined them like that, not specifically so that it works, but this yields such an interplay. And this is fun, right? Alright, and this is cosine alpha. This coordinate, the x coordinate here, the y coordinate here. Alright. Well, now this we use to extend the usual notion of sinus and cosinus, and you probably can already guess how. That's really, the usual, the most natural derived from a triangle. We just extend this notion to this is unit circle. This is everywhere. Unit circle, unit circle, unit circle, unit circle. Everywhere here, of course, here unit circle. Understand? Because this is length 1. And this again unit circle. And you see. By the way, important thing. We always start to count those angles using alpha from here. So here is 0 degrees angle. And this ray of angle lies parallel to x-axis, and then it goes like that in this direction. So we count the angles from here, right? And now alpha, any angle, and test alpha from 0 degrees to 360 degrees. And we take any angle and this angle again counted from here, right? So that would be the angle. that will be alpha. It could be 360 degrees, so it doesn't matter. Right. To this angle, there is a point. There is a point. I don't know, C alpha. V point in V plane, and this is unit circle again, so this angle defines a certain point in V plane. And this corresponds to this. Define. We just extend the sinus and cosinus in the natural way. And sinus alpha. Y coordinate can be also negative, as you see. Coordinate of the alpha, and this is not minus, this is I don't know what it's called, but heaven. This is heaven. And cosinus alpha is defined as x coordinate of the alpha. So you see, it is just a definition, but it's a natural definition because we started here, right? Right. So this definition includes a special case, of course, our right angle triangle, and of course for any other triangle, what you will get if you consider this triangle as how should I put that? Well, if you make the angle of this triangle, like consider such triangle, right? If you make this side, one of the sides equal to 1, then you could put this triangle to here, right? This side is equal to 1, and here it somehow works, right? We have maybe rotated it out of the plane in the 3D space, doesn't matter. So we put it here, and then this would be exactly beta, and this would be exactly beta. And the cosinus of beta, which you compute here, or sinus of beta for that matter, would be exactly that thing, exactly the coordinate in that case. Right. And of course, by size symmetry, we can define now sinus and cosinus of triangles of any size. Doesn't matter. Right. Okay. Now, and the computation in here. Wow. It's just I don't actually know if I know that because I'm just knowing that this works, and I'm knowing that this angle has some sinus, some cosinus, but I wouldn't try to compute it geometrically. You can compute it from cosine theorem, for example. And the cosine theorem you prove here, and the size symmetry gives that the theorem actually holds. Yeah, that's how I would do that. I guess. And well, that way to each angle with sine, cosine, and then we go back to this triangle, and then we know what is sine, cosine of this triangle. But if you, as I said, if you fit this triangle in the right size geometrically, of course this the other side doesn't have to be 1, it could be something, but then you fit it here and you measure that, and of course you have this coordinate because it is just how much we have moved from this line to here, and making 1 makes it makes this leg that measures the angle exactly the length of a unit circle, so it moves like that. So imagine we have rotated this triangle in the 3D interface, so that it kind of looks like that. And then this is the measuring leg, and this measuring leg goes from here, and of course that would be this coordinate, right? But this is how we define the sine cosine generally. Right. Also tangent, similarly tangent, tangent alpha and cotangent alpha. Alrighty. I mean, just as those quotients, right? Alright, now two ways to measure angles. Angles are called so. This is again a unit circle. Actually, you can always see it by this coordinate, which I always write here, right? The radius is obviously 1, and this is x, this is y. And we start again here, and you recall that such an angle gives this length, right? This gives length L alpha. And you recall that we think of this measurement so that the relation exactly holds, ignoring the possible units, so that this comparison might be flawed. We just look at the mathematical numbers that result, right? And this relation to the circumference of the circle here, the relation to the whole angle measured in degrees, allows us two ways to measure angles and to translate between them, right? If we want, if we have angle in degrees, then we can just multiply 360 to this. If we have the length of such a thing somewhere here, then we can easily compute the length of the angle in degrees. In that we simply compute that, and similarly you bring 2 pi on the other side, 2 pi alpha. That is, by the way, another way to justify that by the translation to circles of bigger size it works, because, well, the angle would be still be part, and then this would be also still be part, right? So the relation is always kept, right? Because this is a constant pi, this is a constant 2, and this gives exactly same size symmetry, so this will be enlarged by same size symmetry. I could just say alpha tilde is equal 1, because that would be same part of would make same part from 260, right? And as we recalled, the measurement is only relation to a part or relation to the whole. Yes, nothing else in the measurement. That's exactly that. We just don't think about that anymore. But yeah, originally it's that, and this is where it comes into play for you, right? So and you probably know that in mathematics we just like to measure angles like this, and we like to measure angles like this because it's just that's our way, that's way of mathematicians. And the thing is, the interesting functions like sine and cosine it is unhandy to deal with in degrees because those actually numbers, like real numbers on the real line, right? The things that actually exist in mathematics, but this thing in mathematics, it does not really exist. What's that? This is just number. You can go on the circle, or you can go on the real line. We just identify them anyway. Circle is just folded out. I mean, a real line is just folded out circle. But this, we don't like this. This doesn't make any sense, right? That's why we prefer this measurement. And now you should simply know, and I would not recommend to use some kind of, I don't know, device to do that. For example, this calculator. I would not recommend to use that. Just unit circle. And you know that this angle is 0, and we go around, then at the same point is 2 pi, right? And you just know the coordinate. The coordinate is 0, 1. So you know automatically what is cosine of this angle, what is sine of this angle, because it's just coordinates. And so it goes. For most simple angles, right? Here you started by 0, you go always in that direction. That's a mathematical positive sense of direction of rotation. And here you have pi half. And I hope you can see the coordinate of this point without a calculator. That would be 0, 1. And so with sine and cosine, you just eat here accordingly. And you can even do that. That is by 4. We just have to compute those coordinates. You could compute them. For instance, well, I don't know. You could compute it because this is okay. We could do that now. But I show you the other way, so let's forget that for now. But by 4 it's interesting. I show the other way, the simpler way. We could compute it by analytic computation, of course. Or for example, we would just compute the line x, and we would for the unit circle correspondingly compute circle x. We had that representation, right? And we need the upper half, so we take the angle, and we have that, right? The restrictions, and we would just compute the cutting point of that line x and x, and we would have the coordinates. But I would show you the easier method that you can do anytime. Of course, this is universal method that you can always do, right? Because this is just intersection of a line with a circle, basically what is going on here, right? And well, that you know that the line, how it goes, how the line goes, that this is just the tangent of angle. You should know it from the school, right? I mean, this angle is alpha, and to have that line actually here it is just 1. I just see that because of symmetry, but generally ax equal tangent alpha for lines like I don't know, like that. You see, I just continued drawing that, and that is angle alpha. And you just know you take the tangent and you can compute a tangent alpha ax y x y x. You take tangent alpha, you take this line, you take this circle, and you just compute this, right? So for any angle, you could easily derive what is its. But of course, for nasty angles, you have to compute this tangent. But computing, you have just to know tangent, and then you compute sine and cosine, and here the tangent we see immediately, and we can compute in sine, cosine, and tangent. So yeah, but don't forget that, because I'm really frustrated that people take calculator for that. It's you can do that, but it just doesn't work. That you shouldn't do that. And this is pi, and I hope you know the coordinates of this point in the coordinate system on a unit circle. Or at least if you don't know, of course, I don't know if I know them, but I see them. If you don't see, well, it's just not okay, okay? Well, okay. 3 pi half, again, sinus, cosinus, just coordinates, nothing else. And of course, here pi is for this half of the circle. 2 pi, half of the circle is what? Pi. 3/3 of the circle. 1/4 is pi half of 2 pi. And here 3 pi half. Here 1/4 of the circle is pi half. Of course, when I talk about the circle now, I talk about the circumference, right? Right, and that's how it goes, right? Now, the most important angles, you should be able to compute it. In my opinion, it's a shame to use calculator there. Of course, I mean, if you are not pursuing some studying where mathematics is needed, but if you are not pursuing it, I doubt you would watch my videos. So, well, intend to pursue. You have x, you have y, you have 1, 0, and well, I promise to show you pi 4, right? And by symmetry, just by symmetry, you see that 3 pi 4, just by symmetry, right? I took this part, and here again, divided by 2 parts, and I see the coordinates, right, by symmetry. You don't see it by me, but clearly that is symmetric, because I just took here that part, and I took here that part by 4 back. And so it is symmetric. So if you know these coordinates, you actually know these coordinates. And of course, you know those coordinates. 5 pi 4. Because you just have to keep track of the signs. The absolute values of the coordinates would not change, obviously. Here, 2 coordinates positive. You have computed them. I'll show you in a second how. Here, 1 coordinate is negative, right? But the absolute value is same. Here, you have 1 coordinate negative, this one, another coordinate negative, both coordinates negative. Okay, here you have 1 coordinate positive, 1 coordinate negative, but the absolute values would be always the same, because this is just symmetric, right? So obviously the distance to this will be same if I go on the circle. Same thing from axis, and symmetry of the circle. I go same here, go same here, right? This is how it works. And if a teacher tells you to use calculator there, well, I just can't tolerate that inside. I would hate that myself, but okay. New times, new customs. Well, nonetheless, I would recommend you to do it differently. Okay, now the degree thing, is useful because that way you can deal with triangles easily, right? You have 45 degrees, right? And we only need those coordinates because that. And what does that mean, 45 degrees? Well, that is a triangle with 45 degrees here, right? We have studied that connection, and we can do this triangle, and we see, well, that is 45 degrees. And that is 90, and that is 45, so we have that triangle. And what is about this angles? Well, of course, we have same sides, and this is C. And you know from the Pythagorean theorem that we have proved extensively that we have that. And from that, you know that A divided by C is equal. I'm just computing that, bringing that to that side, that to that side, and whatever, and taking the square root, I just get that. And usually we don't leave it in that stage, we just make here completion and obtain that. That is, this here has coordinates pi fourth corresponds to 45 degrees, yes, corresponds to a point pi fourth with the coordinates, and you see sine and cosine of course equal because it's that, right? And now what coordinates would this point correspond to? Of course you just see, oh, this is positive, y is positive, okay, give you same coordinate because absolute value is same because symmetry. And here, well, that is negative, okay, because here you can compute it very easily, you see. Right. Another interesting value is and you know another reason other than not to frustrate me why you shouldn't use calculator here. That way you get in touch with those things, you get familiarized with them, you internalize them. And this is very important for what I'm about to explain you, and that seemingly isn't explained at every school anymore, unfortunately. This was this point, right? Corresponding to this, like here, I guess. No, I don't know where, but we had that C alpha. Yes, here. I even wrote it explicitly. You see. Okay. So this corresponds to this point and use coordinates sine alpha, cosine alpha. Right. Another point of interest is that one. Okay. This is just pi third into half centimeter and 1/2 of it by 6. Maybe I'm not doing it exactly, but it doesn't matter. Right, again, unit circle, of course. First thing you notice, well, if you have that triangle and you have that triangle, then they are just copies of each other, rotated differently, right? Because by symmetry you have taken here, same thing as here, and this is just the same, right? And you have taken here, and you have taken went away from here by here, so here, and you went away, so you lowered the height by the same as you went here, right? You were lowered the height, this height, so like this height is lowered if you look at that rotating your head, right? So this is in triangles, and so their sine, cosine, of course, like switched. Sorry, that wasn't right, of course. Of course, it was right, but okay, customarily this triangle. Yeah. It's like same thing, because I've shown this, you could take this triangle and you see that immediately, right? But of course, the sine and cosine are of course switched in, right? And so it suffices to consider only one of them. And pi third, what is that? Well, pi corresponds to 180, right? So pi third corresponds to 60. That is, we have let us see, and that is A, and that is B, and now you see this angle is half of this angle. And of course we have again that, but that is of course not all. I don't recall that exactly. Mm, mm, well, I don't recall what was the point in here. Okay. You see, if we draw beside, and we get again the same kind of triangles, right? Because that was already 60, so that is 30. Okay, of course we do. Right, we had that in our proof of the Pythagoras theorem. Because they are similar, of course, and goes the same. No, I think I wouldn't know. Mm, right. Hmm, okay. I would not know how to. Okay, okay, here you have to know some stuff. I wouldn't know how to do that else, and we'll prove it in a second. Oh well, cosines 16 is equal sinus 30 minus cosines 30, of course, no squared. And what's that? Well, for example, if you go here and this divided by c, and that's b divided by c squared minus b divided by c squared. Okay, and that's b divided by c. B squared minus c squared c squared. Alright. Well, I'm not even sure if that is correct. You see, I would have to derive that formula myself. Is there an easy way to see? Let's see cosines alpha. Okay. This is how you derive such stuff. Well, that's one way. That is alpha. That is alpha. And you have sorry. You have to multiply by cosines. And you have just this single. You have that. And now you have the sinus minus the cosines. Right. Sine squared minus cosine squared. Right. Take the sinus, take this here. Take the sinus, take this here. Right. And we have cosines to alpha. Right. And we now have to prove that this is b squared minus b squared. Right. let's say not prove, derive. Why? Because I'm not sure if that's actually correct what I wrote there. Well, how would we try to prove that? Sine squared minus cosine squared seems to be negative to me, and it will be most likely the case because at least cosine is still positive, so it's most likely the other way around. Okay, how do we derive such a relation? Let's think about it. And this cosine of cosine 12. Right. We have to think about this stuff, and we have to somehow that this squared gives a different picture. Okay. Okay. Okay, it doesn't help me much. Well, what I'm trying to do is to prove it analytically. I mean, by calculus. But we are just switching here, right? Right, of course, if we'd like to prove this, we'd like to prove something more general. We are going to prove that for real. And we'd like to consider something like alpha plus beta cosine and sine. Right, you see, we could just do it the way like I suggested. Alpha and we have plus beta, so we have to go for this line beta. Right, and that would be okay. It's not necessarily nice actually. Wow, but okay, it's not necessarily nice. Think about it a little more. Well, let's derive a general formula for let's not call it tangent, call it a line. X E X. Let's say intersection point. An intersection point in the upper half. Right, that is, we have just minus x squared, but I suppose it won't help. X, I believe to already see that it won't help. Here is squared 1 minus squared. Okay, it's really simple. You see, we just have a line for the origin, so that works. And divided by squared plus 1 certainly works. And the thing is, is actually our x doesn't seem to help much yet. It always rise. Okay, I'm not checking this, but we have one solution, and this is plus minus, right? This would be minus, but we have positive solution because we are by positive x coordinate, right? Here, because we are interested in those lines, right? So we know that there is solution, or the solution should be positive, and then this is exactly the solution, right? Right. It's just tangent alpha plus beta divided by tangent alpha plus beta squared plus 1. It's weird enough, right? I mean, we have the coordinates tangent alpha plus beta is equal to x. No, excess is 1 divided by that. 1 divided by tangent alpha plus beta plus 1. And here we have that, right? If we like, this is our sine, and this is our cosine. Alright, if you'd like to actually look at what that is, our sine, for example, and you would have something like sine squared alpha plus beta, and that would be cosine squared alpha plus beta. Oh wow, I see what is happening. But something weird is happening. Cosine alpha plus beta squared. So we coordinate is squared. Why? That's weird. Right. Squared. Right. So nothing interesting is happening. Because we already got it in tangent in that way. Right. This doesn't really fetch much. But let's of course square root out of this, which gives exactly cosine, right? But if this is square rooted, that is a different thing, right? Okay. Now we mention we have square root of this, face. We have that in cosine squared. No, this doesn't give us anything at all. Oh, that's unfortunate. But yeah, I saw it coming. Problem is that we already relate to these hot stars inside, so of course I don't expect to get anything. Of course, we could kind of prove Wyatt-Taylor, but well, we just consider a few coefficients and then try to derive a general formula and try to prove that it converges, and then we would have to define it as sine, cosine. I don't like that at all. You know what I think? I don't like that at all. And that's why I would do okay, let me recall. Yes. But I don't know if it would work. How it would work actually. Alpha plus beta. You know that Euler formula. We will discuss that, so it will be independent of this. No worries. It will be all consistent in that sense, right? And you just have like exactly cosines. But the beautiful thing is that we can now use simply the multiplicativity of exponential. With that, we get in two formulas at once. But well, I'll talk about complex numbers, not about trivial stuff, of course, but exactly about how this works, actually. Actually, not with a proof, because it's not my emphasis in this case, but okay, these formulas I like to prove. And just by arithmetic of complex numbers, we get both formulas. As what? This is also a way to derive them. Right, bulletproof. So maybe coordinate is equal, so that is the formula for cosine. And this is formula for sine. Alright. So I want you to have it one exactly. Alright. Because I want to have that. Right. How to alpha is special case. Yes, that's like I suspected. Alright. Just set beta to alpha equal to alpha. That was nonsense.
was complete nonsense. Alright, that was also complete nonsense. Alrighty. Now we have cosine 12. What is that? That is b divided by c is equal cosine alpha squared. That is alpha. That is that. It's a divided by c. Minus sinus alpha squared. That is b divided by c squared. Okay. I don't see how it helps necessarily. Okay, I see something. No, I don't. Okay, but we have to derive it somehow, right? And I'm not seeing how. Really? Okay, we could go the long way, compute this coefficient and things like that. Like we went by the Pythagoras theorem, right? Compute that, compute a. But must be something simpler. You know what I would do? I would just use this. That is the sinus theorem, right? But we don't have it yet. Oh, it's not a problem. Sinus alpha, okay, not alpha. Okay, if that is alpha, yes, it's beta. Okay, sinus alpha divided by b. Sinus beta divided by a. And how do we do that? Well, okay, sorry, that wouldn't help. Okay, wow, that's great. So, yeah, we could prove that, but it wouldn't help. At least not immediately. I think I'm missing something. That's right, that was formula for cosines. And we already said that alpha was that angle, so let's rewrite it to beta, because we go in the corner B, it's kind of beta. Right, beta. What is sinus of V2 alpha? Sinus of V2 alpha would be
sinus alpha squared. No, yes, sinus alpha squared. No, a sinus alpha cosinus alpha. It's 2 sinus alpha cosinus alpha. Alright. 2 sinus alpha. 2 p h. Blah. That is something interesting. No, wait, something is wrong. No. This is for angle. Because that is actually sinus 60, right? So since that is sinus 60, we get that from the formula, and with that, we just cancel that, and we get C is equal to B. And with that, we finally get something reasonable. Okay, well, I'm not necessarily. Something's off here. I mean, you had sinus and cosinus, and those were worse, for sure. But then you had sinus 60, something like that. Right. Should be like that actually. But something's wrong. Something is wrong. Let us see. This is 4b squared. This is 3b squared. Right. And 4b squared. Right. Right. 4b squared. C squared. No, that's not what we wanted. Okay, that's weird. It's weird. Yes. Right. Sorry. But this doesn't make any sense. Wait, it makes sense. C divided by 4. Yes, doesn't matter, but I'd like to have that. Right? And that gives B divided by C is equal 1/2. So that formula you can use here to compute that. Right. So you should be able to, in my opinion. Maybe like you struggle, but should be able to. Right. And on that, it follows course, since that was what was b, what was beta, we have to look. Right, that angle was beta, and then that was b divided by c. Right. B divided by c, and that was 60. Right, and that was for science. But well, that is wrong. Oh, b divided no, b divided by c is with cosines, right? And this was with sinus, and this is cosinus, right? It's cosinus, that is cosinus, and that makes sense. Ah no, not yet. Cosinus 60 degrees. It is really equality because we only compare the single relation, right? Is equal 1/2. This makes sense because for 60 we have pi third. This is over here, and cosinus is more than the sinus, right? This is 2 above, right? Right, that makes sense. That makes sense. Right. And now the other guy. The other guy is just oh, know what the other guy is. We have -1 minus. Oh, I don't like that. I don't like that. -1/4. Ah, okay. No, that's okay. And you have that sinus of cool. Of course, in general, plus minus, but we have now here an angle in a triangle, so we know where our sinus lands. The coordinate, that is the coordinate. Remember that sinus is a coordinate. And well, we are here, so sinus positive, so minus doesn't matter. In this case, I have just computed it, right? And this is not alpha, of course, this is beta, because I computed that for beta. Right, so sinus 60 degrees. Equal. So that makes sense compared to that, because square root of 3 is certainly larger than square root of 1. That is 1, because we have monotony. We have that square root is monotonically increasing. Right. And with that, we have that. Right. Where was it? Here we are. And this coordinate turns out to be cosinus. Okay, we computed actually here, right? And we had 1/2 in the cosinus. The small one makes sense, right? And here they are switched because of symmetry, right? I mean, this corresponds to this point. I thought it corresponds to this point. This corresponds to this point. Right, pi 6 corresponds to this point. Right. And of course, same game. This would be what? This would be 4 pi third. 4. Sorry. That would be 3 pi 6. Just calculating with fractions. It would be 4 pi 6. be same as 2 by 3rd. And the coordinates, well, you can guess the same game with symmetry. Again, here, and here, and here, and here, with corresponding 11, b6, or whatever. Right. Well, I wanted to have it all done, but there was a lot to prove, and to my shame, I had problems with Pythagoras and the problems with his formula. Of course, not necessarily to my shame, but well, I mean, it took time because of that. Right, next time. We have to prove something. I have to prove yet. What we use here, what we used there, right? By this last computation, I have to prove yet. Cosinus alpha. Well, one proof is just use 3 Pythagoras in the triangle with the radius 1. You know that this cosine alpha, you know this sinus alpha. And this is how you compute that thing, right? So you just use this. And this is just the Pythagorean theorem, right? In our proof, in the right angled triangle, which is basically the same, just normalization done explicitly. A squared plus b squared equals c squared. Okay. And that was a proof, and next time, in this series of videos, because I also have our series, so it's just for this series that it is next time, necessarily really next time. Well, have we done that? Okay, trigonometric functions. Brought from unit circle to the coordinate system. Its functions. Well, as you well know, I hope cosine, whatever, right? Here's trigonometric functions. And of course, for that, we have first to know what is actually inverse function and how it works and things like that. Right. What else? Why actually these that are complex numbers? Visualization. And visual trigonometric properties. Okay, I think that would cover all that I wanted to tell you in that regard. Of course, there are some fun identities to discover, but that you will do yourself. I suppose this was quite a challenging run, but I hope that you could follow more or less. Anyway, certainly really interested people who would have followed through it. Right, yeah, I'm not trying to somehow make it easier for you, in that I leave out things like that. I hate that. I rather start a proof and finish it differently and get a different idea than not show you something. Everything should be shown, brought into place. And if you don't understand it now, they will come when, hopefully they will come when you see that there's a need, that you have this need to really understand things, not just to take it in and as if everything is alright like that. Right. Alright, I think it's all points that I need to do next time. And we have then covered this topic in its whole extent, actually, yeah. So what you would need to know about that, or at least we will have touched it. You have that. You also know how to prove trigonometric identities. Oh yeah, I think it will suffice to alleviate my disappointment how this is usually done nowadays. Right, okay. Next time we'll do this. Next time in this serious videos. Okay. I'll stop here.